Hi everyone, this is Mrs. J, and today we're going to learn about the fundamental theorem of algebra. But first, please pause the video and give this warm-up a try. All right, go ahead and check your work here. So the rational root theorem gives us these possible for zeros, so you can start using synthetic division to check. Make sure you have that zero placeholder for the missing x squared term. If you check x equals 1, you find a remainder of 0, so that's one of our solutions. And the remaining polynomial can be factored, so you get x equals 1 again. So since you have it twice, it means it has a multiplicity of 2, and you have x equals 2. So you have 3 solutions. This one is counted twice. Here's how you can find the y-intercept to replace x with 0. And remember, when you have a multiplicity of 2, you have a touch and turn. So the right side goes up because my leading coefficient is positive. The left side goes down because odd degrees have opposite end behavior. So we touch and turn, and we go through our intercepts. So today we're going to keep solving equations, but now we're going to work in what's called the fundamental theorem of algebra. So here's the fundamental theorem of algebra. It says that if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution. And in the set of complex numbers. So this is really not anything super mind-blowing. It's essentially saying all polynomial equations have at least one x-intercept. And it can be real or imaginary. So the corollary is actually a little bit more useful to us. What the corollary is saying is that if a polynomial has a degree of n, then the equation f of x equals 0 has exactly n solutions, provided that each solution repeated twice is counted as 2 solutions, 3 is 3 solutions, so on. So multiplicities are counted multiple times, and imaginary solutions are counted. So what does this mean? The degree tells us the number of solutions to expect. Counting multiplicities and imaginary zeros. So there you go. So we can use this to help us make sure that we have found all of the answers to our problem. All right, let's give this one a try together. So looking at the degree of our polynomial, I see that the degree is 4. So I should expect 4 solutions. They can be real, imaginary, repeating, but there should be 4 solutions before we're done. So let's use the rational root theorem to give us a list of potential answers. So it's essentially just the factors of 8 over the factors of 1, so plus or minus 1, 2, 4, and 8. So let's say I try x equals negative 1. I'm going to list out my coefficients. I am missing an x squared term, so make sure you have that placeholder. Okay, drop your first term, multiply, add, multiply, add, multiply, add, multiply, add. And here we do have a remainder of 0. So that means that x equals negative 1 is one of my solutions. Maybe I'll write it up here. X equals negative 1. There's one of my solutions. So now I'm going to look at the remaining polynomial right here. And I have x cubed plus 0x squared plus 0x plus 8 equals 0. So hopefully we can look at this and recognize that this is sum of 2 cubes. So remember, a cubed plus b cubed is a plus b times a squared minus a times b plus b squared. So I can see that my a value is x, my b value is 2. Remember, this is b cubed, so the cube root of 8 is 2. So we get x plus 2 times x squared minus 2x plus 4 equals 0. So here we can use the zero product property to help us solve. So here we get another solution. We get negative 2. So I'm going to add it. I'll write it up here so we have all of our lists together. So the remaining quadratic here, you can try to factor it, but it's not factorable. So we have to do something else. For this one, we should use the quadratic formula. So x equals negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So let's simplify that out. Positive 2 plus or minus 4, positive 4 minus 16 all over 2. So here we have 2 plus or minus the square root of negative 12 all over 2. 2 plus or minus, well, 12 is 4 times 3. So we're going to have square root of 4, which is 2. We put an I out front because of that negative, and that is why we weren't able to factor. It's because our remaining solutions are imaginary. Now, both of these terms are divisible by 2, so let's simplify it into this. So 1 plus or minus I root 3. So these are going to be my remaining two solutions. X equals 1 plus or minus I root 3. Remember, that is two solutions because of the plus or minus. So you can see here I have two real solutions and I have two imaginary solutions, which gives us 4 total solutions. So now I know that I am done and I've found all the solutions to this polynomial equation. All right, let's try one more together. So again, I'm going to use the rational root theorem to help me generate a list of answers. It's going to be the factors of negative 8 over the factors of 1. So same as last time, actually, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So from here, let's try negative 1 again. I'm going to list out my coefficients, noting that I am missing an x to the 4th term. Negative 12 and negative 8. Okay. So I multiply and I add. I multiply and add. Multiply, add, multiply, add, multiply, and add. So I have that 0 placeholder. So that means that x equals negative 1 is a solution. So now let's look at what we have next. We have x to the 4th minus x cubed plus 2x squared minus 4x minus 8 equals 0. So here I'm looking at it and I say, well, looks like I'm going to have to do another round of rational root theorem. This will give us the same possible answer, so now we just keep checking. Let's check another one. Okay, let's say I check, positive 2. So here we have our coefficients listed out. We multiply and add. Multiply, add, multiply, add, multiply, add. So we have another 0 remainder. So that means that x equals 2 is another solution. I'm going to put it up here and box it. And I forgot to list this. We see that the degree of our polynomial is 5, meaning we should expect 5 solutions. All right, now let's look at what we have left. We have x cubed plus x squared plus 4x plus 4 equals 0. So this, let's see if we can factor it. There's 4 terms, so I can try to factor by grouping. I can group my first 2 terms and my last 2 terms. So here we have a GCF of x squared. So I can do x squared times x plus 1. Here we have a GCF of 4. And we do see that common factor of x plus 1. So we can factor by grouping. All right, let's finish this off with zero product property. We set each factor equal to 0. Here I get x equals negative 1. And here I'm going to isolate. I'm going to take the plus or minus square root of both sides. And here we have the square root of a negative number, which means we get an imaginary number. So we get plus or minus 2i. And there's our remaining 2 answers. So We already had -1 here. We have another -1, so I'm going to list it again. So it has a multiplicity of 2, and then we have 2, and then we have x equals plus or minus 2i. So again, even if you get the same solution twice, we got -1 here and -1 here, we count it as two separate solutions to make sure that the number of solutions adds up to our degree. So we have 1, 2, 3, 4, 5. So there you go. So we can use that fundamental theorem of algebra to make sure that we have all of our solutions. All right, go ahead and pause the video and see if you can try this one on your own. All right, this is definitely a tricky one. So we have a degree of 4, so we need 4 solutions. So with rational root theorem, there's 4 options for us to try, plus or minus 1 or plus or minus 5. Let me have the plus or minus. So if you try -1, you'll find a remainder of 0. So that's one of my solutions. This is the remaining polynomial. It's not factorable, so we have to do rational root theorem again. We have 4 options to try. So this time if you try +5, that will give you a remainder of 0. Then, if you look at what's remaining, x squared minus x minus plus 1, this is not factorable. So if you have a quadratic that's not factorable, you have to do the quadratic formula. And that's how you get the last 2 solutions. So you have 2 real solutions and 2 imaginary solutions. All right, I have another one for you to try. I gave you a little hint to give you a start of which x values will work for your solutions, but pause the video and give it a shot. All right, go ahead and check your work here. This is definitely a time-consuming problem. It takes multiple rounds of synthetic division. So here I tried +1 first. You could also have tried -2 first, that's fine. We have that remainder of 0. Here's my remaining polynomial. I need to do it again. So I tried -2, remainder is 0, so it's a solution. This gives me my remaining polynomial, 1x cubed plus 2x squared plus 9x plus 18. And then I have to do another round of rational root theorem. And then I tried -2 again. Remainder is 0, so it's a solution. And I was left with x squared plus 0x plus 9, so x squared plus 9. Now, as soon as you get down to a quadratic, we should be able to finish solving completely on our own or without synthetic division. So this one, I just used the square root method. I isolated x squared, and then I took the plus or minus square root of both sides. Okay, let's take a break from solving and try a more conceptual problem. Here we have a graph of a function and the degree of the function. So based on the graph, we need to determine how many imaginary zeros must exist for the function. So I know if the degree is 3, I should have 3 solutions to this problem. So I know that if there's an x-intercept like you see here, that's a solution. Okay, so here you can see that I only have one x-intercept for this graph. So that means that I only have one real solution. So if you have to have 3 solutions total because the degree is 3 and you only have one real solution, that means that we must have 2 imaginary solutions. So you can also use that fundamental theorem of algebra to tell you how many more solutions to expect and what type to expect. All right, let's look at this one. Here we have a degree of 4, so we need 4 solutions. Here I see 2 x-intercepts. However, there's something that maybe you notice about them. These are both touch and turns, right? These are touch and turns. And we know that a touch and turn means that the multiplicity is even. So these actually each have a multiplicity of 2. Well, they could have a multiplicity of 2 or 4 or 6, but if one of them had a multiplicity of 4, then you wouldn't have any more x-intercepts because then it would go over your total degree. So that means that this must have a multiplicity of 2, and this must also have a multiplicity of 2. So that means that we already have 4 real solutions, which means we have 0 imaginary solutions. So sometimes you have imaginary solutions, sometimes you don't. Okay, the last thing we're going to do is we're going to see if we can create a polynomial function given the zeros listed. So here they're asking for the least degree possible with rational coefficients and a leading coefficient of 1. That means when you go to turn the zeros into factors, don't square them, don't add in anything extra. It should be the smallest degree possible. So I'm going to call it p of x. So if I have a 0 at 1, the factor would be x minus 1. If I have a 0 at 2, the factor is x minus 2. And if I have a 0 at negative 3, the factor is x plus 3. It's like zero product property backwards. And then here we are going to want to expand it out. So I'm going to start by multiplying out my first 2 binomials. X squared minus 2x minus 1x plus 2 times x plus 3. Let me simplify that. And then we just have to do our last round of multiplication. Maybe here I'm going to go back and use that box method that we learned at the beginning of the unit. So we have x squared minus 3x plus 2, and then x plus 3. So x cubed, negative 3x squared, 2x, 3x squared, negative 9x, and 6. Then all we need to do is combine like terms. So here and here. So we have x cubed, and then we actually have 0x squared here. And then this gives us negative 7x plus 6. There you go. Okay, here's the last one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work really quick. So first check that your factors are correct, and then it's just a matter of multiplying and expanding out those factors. All right, that is all for today's video. Thank you so much for watching.